Hello everyone and welcome to Handmade Hero, the show where we code a complete game live on stream. We are trying streaming from the new office location, so it's a little bit tricky. I'm not sure whether or not this is going to work exactly. We tried streaming for a while before starting the stream here. It was a little bit dicey. Initially I thought it wasn't going to work, but then it turned out that it was just Comcast was gating our speed in a weird way that they weren't supposed to, below what it was supposed to be. But rebooting the cable modem seems to have fixed it, and so it maybe it's working okay now. I don't really know. It's a little bit suspicious, and it's one of those things where I'm probably going to have to give them a call and find out, because I'm afraid that it's something that may be happening periodically, in which case we're going to constantly have to struggle with it. But we're going to give it a shot, and we'll see what we can do. We'll see if we can get some programming out of it, and who knows. So anyway, here's day 403. We'll do the best we can. If it turns out the recording here locally, as far as we know, works just fine, obviously. So if something happens to the stream partway through, I do apologize. We'll just assume that you can catch the video on demand when it's posted up on YouTube, right? So let's go ahead and get started. Today is day 403. I'm going to go ahead and open up the code base here. It's been a while. I don't know why this keeps... Okay. There we go. Didn't really want that window hanging around for the entire time we were going to be programming, so it's good that we were able to get rid of that little thing. Anyway... so let's go ahead and run it. We were in the middle of playing with lighting, and at the moment we are in a reasonably good position with lighting. The problem is we just need to start working out how we're going to propagate light in a reasonably high quality way. So at the moment we've kind of got this little lighting test that's running entirely on the CPU side now, so it's not particularly good in terms of speed. But we're just trying to get to a point where we can verify that the quality is roughly what we want it to be. And that's going to require us doing a little more thinking about how we're transferring light. You can kind of see that at the moment, it is at least working to a certain extent. It's not a great lighting solution, but we are at least, what we're looking at here is just sort of block lighting. In fact, I can... show you the actual lights here in a second. Let's see here. Here we go. This is actually what we're simulating here, just these little sort of light reflectors. And what we don't really know at the moment is exactly how we want to transfer light between them. We've sort of done a few things. This right now is using a sort of stochastic, like a ray casting technique, that's just looks at different reflectors versus each other, sees how much each reflector can see each other reflector in a sort of like randomized fashion, and then propagates the light around. And as you can see, some of that stuff works pretty well, actually. And at the speed that it's running now, probably we would actually even be able to... once this is running GPU side, this is probably actually fine, as weird as that seems. So, speed-wise, we don't even really have that much of a problem at the moment, I don't think. But what we do want to do before we go any further down that road is just try to do something with the quality. So there's two ways we can sort of go about looking at the quality at the moment, or rather, I shouldn't say two ways. Perhaps the right way to say it would be, there's two things we need to look at in terms of quality at the moment. And one of them is just the fact that we're not really taking much care in how we're transferring light around. And obviously that's something we can sort of start to improve by tightening down the equations, and doing a more sensible approach to how we move the light. But the other thing that's particularly interesting here is we have not yet put in anything that operates in a multi-resolution fashion, and we're going to want to do that as well, even just for quality. And so let me go to the Blackboard, assuming that the Blackboard is working here. I assume I reset up the pen properly. Don't actually know that I did, but we hope that I did. Okay, it looks like I did. So today is day 403, is that correct? Oh man. So it's so interesting. We really need to track down that Milton bug. It's like when Milton loses, like when that thing pops up in front of Milton, it loses the ability to access the tablet. I have no idea why. And it's not repeatable either, right? Like there it is, here we go, and there it is still. So, you know, it wasn't a problem that time, you know? Anyway, so let's just talk about multi-resolution and quality in terms of lighting. So what we have right now is we've got, you know, if I was going to look top down here, you know, we've got some stuff that looks kind of like this. We've got these little reflectors, and what we're seeing is we've got these reflectors that are sort of casting rays out to see what they can hit, right? And obviously the quality of the light transfer is, you know, besides the equation that tells us how much light we want to transfer when we actually see another reflector, we obviously have a number of issues there which are just related to how many of these rays we shoot and in what direction will materially affect the quality of our solution. Because, you know, no matter, we're not going to be able to shoot out like 1 million rays, right? The number is not going to be high. It's going to be like, you know, 8 or 16, or at best on the GPU, something like 256 if we got really obsessive. But whatever it is, you have to remember it's trying to encompass an entire hemisphere, right? And a hemisphere is an entire three-dimensional shape, and, you know, 16 samples, even 32 samples, just isn't a very dense sampling of the hemisphere when you start to think about just how wide of a net it has to cast. And to give you some understanding of exactly how ridiculous it is, I mean, imagine if you were not going to have any kind of intelligent handling of casting through the scene, and you wanted to have a situation where you were just going to simulate, let's say, sunlight or something, right? Well, if even in 2D, right, if the sun is, you know, this sort of thing way, way off in the distance, then if you just cast even just a little bit to either side of it, right, you would miss. Because the sun is so tiny and it's so far away, the chances that you'll aim directly at it with a random sample are actually very low. And so no matter how many samples you take, unless that number is in the astronomical, up to an astronomical level, you're never going to hit it. And that is why different techniques are used for sampling light sources and things like this that have a low probability of being hit. Oftentimes what you'll do is you'll intentionally aim right at the light source. So when you're picking which directions to send rays, oftentimes you'll send one directly at the light source intentionally. And that's like one of the cheats that you do, and it's one of the things that allows that to happen. However, one of the problems here is that only works when you know ahead of time what a light source actually is. And so that helps you for emitters, but what about secondary emitters, right? It doesn't help you at all for those. So what happens is, if I have like a really bright light source over here and it's shining in this direction, yes, it may help me to grab it. By knowing that it's an emitter, I can always check to see if I see the emitter and waste a ray on that all the time. But at that point, this guy who can't see the emitter back here, he's going to try to look around his scene, and he doesn't have any special knowledge that this is a place where a lot of light's going to be coming from, because it's the thing that has the primary bounce from this light source, which may be where most of the light's coming from. So that, again, is a problem where you don't necessarily know where you should be focusing your attention. And this becomes a more significant problem as you try to do more sort of global illumination schemes that involve those secondary bounces, because you never know where you should be looking to find out. Now, sometimes you can use hybrid approaches that are like forward schemes, and that may be something that we will do. What that basically entails is saying, well, okay, let's say that we take the light source, let's cast outward from the light source instead of backwards from the reflectors, and let's just tag anything we hit. So when we come out here, we'll just tag like a bunch of things that we hit, you know? And those will now become our secondary light sources, right? That allows us to know sort of a set of places where we should probably be concentrating our efforts in terms of looking for light. And that's a good strategy, and like I said, we may use something like that. But there's another strategy that we probably need to use, and that is the multi-resolution approach. And the multi-resolution approach is just saying that, well, look, we know that when we start to cast these rays out, when we're very close to the surface, we probably have a really good sampling. If there's a light right up here, we know that most of our rays are going to hit it. So we don't have to worry about sampling the hemisphere very densely, because most of those rays are very close together when you've only gotten, say, a foot away from the reflector surface, or an inch away, or something like this, right? The closer, the better for keeping the hemisphere nicely sampled. But what happens, and the part that we're most concerned about, and you can see it here in 2D, is as I send rays out further, right? What may be a very dense sampling in here becomes a fairly sparse sampling out here, and when I get, far enough out, it becomes a massively sparse sampling. So, there's gigantic gaps in the sampling as you get further away, and that's just the nature of a radial distribution. A uniform sampling of an angular space just produces coarser and coarser samples as you expand the radius of the sampling surface. That's just, you can see that very intuitively. There's not a lot of mystery to it. That's just the way it goes. So what that means, and the reason why I bring up multi-resolution, is that no matter what you do, it really doesn't matter what you do. Even if you have sort of a forward scheme like I was talking about with the light sources before, or if you send out a ton of samples, it doesn't matter at all. You will not get a good result for faraway things unless you have some kind of strategy that takes into account the fact that when you get out here, you want to use a more coarse representation of the world so you can find out what's probably going on, right? And what I mean by that is, if I have, some reflectors out here, like this sort of thing, and I'm casting out into them, what I really want to know is I don't really want to just miss these like so, right? Or maybe only hit this one and never hit these other ones by all these three rays. What I really want to do is form an aggregate reflector that's fairly large that just says how much these generally would reflect from how far away they are. And that way all of these samples will hit it, right? And in the best possible world, you have roughly a one-to-one correspondence of what the rays you're sampling and how you've compressed your geometry so that each sample does a maximal amount of work. But, anywhere close is probably fine. So when you look at that, hopefully what that, sort of indicates is that sort of an LOD scheme, right, a level of detail scheme like we normally would do, where we are collapsing nearby things that are similar together, is exactly what we actually want for lighting as well, because when we are looking off in the distance to say how much light is coming from a relatively far away piece of geometry, we don't really need the exact answer for diffuse lighting. For specular lighting, we might want the exact answer, because if we're a mirror or something, we want to know exactly what we hit, right? But for diffuse lighting, that's not what we want. We just want to know the general amount of light and sort of what color it is from that direction. We don't need to know specifically what's going on. So what we actually want, again, is something that operates very much like a cone, right? That collects all the things in this area. And a cone is relatively hard to deal with, so preferably what we would like to do is be able to sample just, say, a line in a direction, and that line instead... I'm so yawny lately. I'm not sure why. I guess I haven't been getting enough sleep? I don't know. I think it's more that my schedule got shifted up because it's brutally hot here in Seattle. Like, not maybe necessarily by the standards of other parts of the world that are more tropical, but in Seattle it's usually relatively cool, and you know, we don't have 100-degree weather days here. That's not a thing. It's not like, you know, Phoenix, Arizona or something like this. And what we've been getting lately is sort of a heat wave where the temperature is up above 90 every day, and supposedly it will be up above 100 even occasionally. And it's awful. I don't know how anyone ever gets any work done with these kind of temperatures. It's just, oof. Gotta buy an air conditioner now. Most places in Seattle don't have air conditioning, specifically because you didn't really need it. So people's homes typically are built without any kind of central air conditioning because it just wasn't necessary. And apartment buildings often don't have it, but they're starting to build them in now because the temperatures are getting so much hotter. Anyway. So what I would like to explore in terms of the multi-resolution stuff is I would like to figure out a way to maybe take reflectors that are nearby and pointing in a similar direction. I would like to figure out a way to sort of condense them down a bit, if possible. Now, it's always kind of a dicey proposition to do these sorts of things because when you're talking about coarse approximations to things like reflectors, you run the risk of producing erroneous lighting results as well, so it's kind of a little bit tricky, and I don't necessarily pretend that this is going to be a straightforward process. But in general, we do need to do something, so I want to kind of look at what our options might be. Now, what I'm trying to say here again is that what I want to do is I want to be able to cast rays out from, say, a reflector and be able to treat these three, for example, as one reflector and just get the sort of aggregate lighting back, right? That's what I would like to do. And that requires sort of a some kind of a tree or a hierarchy of these reflectors where I can sort of go in and say how they are related to each other, how like smaller ones relate to bigger ones. And that's going to be take a bit of doing. And again, the primary problem here is just figuring out how to make these reflectors behave in ways that will not produce highly erroneous results when sampled in the multi-resolution context. Meaning, we want something that will sort of approximate what those reflectors would actually have done if sampled more densely from the place where we're casting. And I don't really know, again, exactly how hard that's going to be. Flipping back to the running version of the program, you can kind of see that since all of our stuff is rectangular, and we generally know that that's how it works, it does sort of mean that we could, I suspect, if we decided to switch, we kind of use a disk approximation for reflectors now. Since most of our stuff is actual rectangles, we could decide to switch to actual rectangular reflectors. If we did that, it is true that we could probably merge things fairly cleanly. Like if you look at how these things are currently laid out, you could easily imagine taking, this entire blue wall and replacing it with one reflector, this entire white floor, replace it with one reflector. Sort of the degree to which these things can be merged up is probably relatively sane. There's not a lot of oddity to it there. But if we remain with disks, that may be more difficult. And the reason that it would be more difficult remaining with disks is because a lot of the things here, like for walls and such, are not really capable of stretching in both directions symmetrically like that. If you imagine, for example, trying to fit a disk to these blue wall here, right? And I guess I can make it even more obvious if I go down to, where is it? That's not what I wanted. No. Render, lighting, show, reflectors. So if I come here and you just kind of look at what we've got, if you imagine trying to make a single reflector that encompassed these three, you know, it would have to be this big thing. It gets a lot higher and a lot lower. It produces a much bigger span in Z than we ever would have wanted it to. And so that's kind of an issue that we wouldn't have if we had something that could be eccentric. You know, we could stay with disks, they would just have to be ellipses, but it seems like at some point you just have to ask yourself, well, if you're going to be starting with mostly quads, why not stay with quads? Which is a very reasonable thing to say, and it's also worth noting that quads are pretty easy to quickly test for. It's not that hard to do ray intersections with quads. It's just three or four edge tests for triangles or quads, right? Once you find a point in the plane, you can then see whether or not you're inside the edges of the quad with just a few edge tests like you would normally do. Now, one of the interesting things about that is there's also a lot of ways that people have found to accelerate those sorts of things. There are actually ways of doing faster testing than testing the point, you know, actually doing the full point test in that way. But I guess what I would say is, you know, we don't probably have to care too much about that stuff at the moment. So we can just treat it like we would be treating any other sort of point and quad kind of scenario. So I think that's everything I have to say about that. And so what I would like to do is maybe go, all right, let's try to think of a structure that we can use to do some ray casting that will be multi-resolution. And I don't really know exactly how we want to structure that hierarchy, but I guess what I would say is I probably want something where I at least have 2 discrete levels of detail. I don't know if we need 3, but I'm thinking of a very straightforward and relatively simple system here, where if you imagine that the world, you know, is in some kind of a gridded layout, which we've already thought we're going to need for other things anyway, so a lot of this stuff maybe eventually can be collapsed into one sort of spatial structure for a lot of different purposes. If we're lucky, who knows? But if we take a look at the world and we say, well, okay, you know, maybe if a reflector is going to be evaluated, it evaluates like its local neighborhood of 4 regions using actually the real reflectors that are there. And then it evaluates the rest of the region, right, the rest of the world using the higher resolution reflectors, right? And if we were going to do that, then, you know, there are still issues that we have to address if we do something that way. So it may be that that's not necessarily the best way to do it. In fact, now that I think about it, that's probably not a great way to do it. Now that I think about it, the reason that's not such a good way is if you think about what's going to happen here, if we start to create larger aggregate occluders, those occluders will perhaps encompass some of the things we already checked. And then we'll sort of be double counting them in these weird ways. So I don't know, that might not be so good. So it might be better to just build them in sort of a more tree fashion, kind of like the paper that we looked at initially was sort of doing, where it says, all right, there is one reflector, right, and that encompasses everything in the world. And then it breaks down into, you know, some set of smaller reflectors. And those break down into some set of smaller reflectors. And maybe each one of these has a bounding box or something, right? Maybe each one of these stores the bounds of all of the things that were sucked up into it, right? And so then what we do is we just start at the top and we say, okay, we've got the boundary of this thing. We test to see whether or not, you know, how far away are we from this boundary, right? However far away we are from the boundary, if we're far enough away, we just use that. If we're not far enough away, we descend one level, right? That seems relatively sane to me. I don't know. That seems pretty good. And I mean, there's no reason that can't operate on the GPU relatively effectively. One of the problems with hierarchical things on the GPU is that the warps get out of phase. So, for example, if we're going to cast multiple rays at a time, or who knows how we'll actually be implementing this in the GPU, or even if you're implementing on a CPU for that matter, you end up in a situation where you want to be able to cast rays together, but different ones of those rays are coming potentially are going to hit different things in the world and be at different levels of resolution. So you end up with different data structure levels that you're accessing, which can be ugly. So it's a little bit hard to say right now what degree of, how problematic this is going to be for us. The other thing we could do here is we could go, again, with a more octree-like approach. So the other option is to say, let's not merge reflectors or think of reflectors in that way. Let's instead think of the world as more of a voxelized structure. And again, that one is more if we want to do tracing out into the world as ways of sampling the lighting as a voxel, right? The reason that that is useful to us is because if we assume that something is voxelized, just using the top-down version here, which would be a quad tree, you can imagine something that looks like this. If I am a reflector here and I'm trying to calculate what my lighting is, when I cast out, like so, what I can do is I can take samples into the octree at various levels, and when I take those samples, what I will find is I will get, if I change the level of resolution I sample at as I go further out in distance, then I will naturally sample a coarser lighting solution when I'm farther away, right? Sampling at the first subdivision level here, second subdivision level here, third here, fourth here, fifth here, right? The problem with that is, again, I don't really know to what degree we can really rely on a voxelized lighting solution for the world in that way. It's pretty tricky to really think through how you're going to make that work efficiently, whereas something that is more straightforwardly based on actual flat surfaces tends to admit itself a little more cleanly to doing sort of radiosity solutions like this. So I don't know about that. But this seems like a reasonable thing to do. So if we wanted to be able to do that, all we really have to do at that point is have a way of collapsing these things up into some kind of uniform structure. Now, one of the things that we're suffering from at the moment, and something that I would like to fix, and probably the first thing we'll do today, or perhaps the only thing we'll do today, I don't know how much time we'll have, we start at 1, so we have an hour and a half. One of the things I'd like to do today is fix a problem that we have been having. And that is that if you take a look at this, for example, if we're still running this lighting solution in real time, but it's not a real-time lighting solution right now, right? It's getting 130 frames a second or something like this, right? That's just not usable. And it's preventing us from trying things that might be even more expensive because it just wouldn't even run, right? So what I need to be able to do, or what I would like to be able to do, is I'd like to be able to turn this into what is essentially an offline lighting solution. Meaning I would like to be able to just, hit a key, run the lighting solution, and if that lighting solution takes 30 seconds, that's fine. It then saves that lighting solution and allows us to inspect it. The reason I want to do that is because I don't want to keep fighting the time budget to get something usable, because what we're trying to do here is experiment. And maybe I want to see what happens if we cast out an absurd number of rays. But for example, if I want to do that right now, and this will be hopefully a good motivating example, if I wanted to do that right now, I don't remember where lighting test is. There it is. We know how many of these ray samples we're sending out here, right? We've got that. Where is that? Here it is, right? We've got that here. We cast out 16 rays. Let's say I wanted to cast out 64 rays, just to see how much better the lighting solution would get, or what the result would be of the lighting solution, right? Well, it's almost impossible to use, right? It's so slow at that point. And then if I keep going further to the thing that I said originally, which was 256 rays, it gets pretty much completely unworkable, and it's just, it's just not usable, right? I mean, look. The thing doesn't even get like 2 frames into it. So I think what we want to do is something very different than this, right? What we want to do is something that allows us to run this lighting solution, and it doesn't matter if it takes 5 seconds, 10 seconds, 30 seconds, it doesn't matter. It will then just cache the lighting solution and show it for us later, right? That's what I want to actually do. So what I'd like to do, like I said, is figure out a way to make that work. And I think we can figure out a way to make that work because, as just a simple test thing that's inserted in here, we should be able to cache what we were going to output as the lighting solution and output it on top of whatever was going to happen before. So something like, if recompute lighting, then you do this. And then another if here, which is like display lighting. And we would put in whatever the code is that we need to put in here. And what I want to do is just take this platform stuff that we're sending down for video. Let's see here. Here we go. We know we've got this game render commands struct, and we know that we could save the contents of it and put them back in later, right? So if we wanted to, we could create a place for saving this stuff, and then we could go ahead and push it forward. So I think all I would have to do, and again, this when we get the render group here, we are capable of extracting this information. So for example, if we just keep this out here. Well, actually, you know what? Now that I think about it too, I guess I don't even really want to do that. I guess I can do this sort of as something that, well, I'm trying to think of how I want to do this. You know what I think is even easier is to not even bother doing quite that much work. Now that I think about it, all we really have to do is we were already copying the lighting out into this push buffer. Why don't we just not do that? And instead, why don't we just save these lighting elements? Then what we can do is, instead of actually rendering the world, we'll just render the lighting elements, and we'll just make that be an option. That seems a lot more straightforward and doesn't require us to do any of that other work. So yeah, that seems easier. So let me just go ahead and put the lighting elements in here for now. And we'll just make a thing called lighting solution that happens to have all these lighting elements in it. Like so. And I guess since we are going to be dynamically allocating this in general, I suppose we could also make it so that this lighting elements thing, well, actually, I guess we don't even need to do that. It doesn't matter. So what I could probably say is, all right, let's take lighting elements equals solution elements. And we know we're going to have as many elements as there are quads. So I'm just going to store that value in here. Something like this. And so what this will do now is this will basically store the lighting test into a permanent buffer. And then what we can do is we only have to run that lighting test when we actually want to recompute it. So for example, right here, we can call if lighting test, and then here we can do another thing where we do an if as to whether or not we want to output it. And that outputting then, where we do copy lighting out here, that can become a separate function that does not have to include computing the lighting. So outputting the lighting and computing the lighting can be totally different, right? So then what I would want to do is I'd want to say, all right, this whole situation here, where we're doing simulation and any of these other sorts of things, right? That should all pretty much just be predicated on whether we actually want whether we actually want to do any new work. And instead, what we would do if we didn't want to do any of that new work is we would do the output lighting instead. So something like this. So that way we can have like a key or something that we push. It will then, recompute the lighting based on whether or not you pressed that key. And then the output lighting will be a state that we can put ourselves in where we're just viewing the lighting, and off we go. I think that's pretty good. So what we need to do here is we want to essentially transform, what we were doing before is sort of hijacking the quads and putting those in there. So, we were taking the quads that we had before, and we were going to write the lighting on top of them. We pretty much want to step back from that, and we want to be able to make something here which we may want to save enough information to reconstruct the full state of the quads as well, and I mean that's not too hard to do, but we want something here which will recreate them from whole cloth, basically. So it's going to be something that's just doing push quads and writing out those quads directly. So in the render group, we're going to want to essentially do this, I think, where we just call this directly. And we do the push quad for each one of our lighting elements, right? So really at this point, We want to loop over our elements. And we want to get each one of these elements in turn. Oops. For each of those elements, we're going to want to do a push quad for the element. And what you can see here is we don't store in the element right now enough to reconstruct exactly what the thing was that came in. And that is not necessarily a problem, because if we only wanted to show just the lighting itself, then we wouldn't have a problem. But if we want to see the lighting on target, meaning with the bitmaps and everything else, we're going to need to have that as well. So what we want to do is store those things down here, I think, in addition. Something like this. And then what we want here for colors, we probably have most of these already created. The emission we don't care about because emission is not currently used by the render. It's only used by the lighting solution. So obviously we don't need to worry about that right now. However, the so this is what our lighting would actually be. Of course, we really kind of want both of these things. So I suppose we're probably going to need to keep most of this, right? So really this stuff probably just wants to stay in place for the most part. Oops. And this can kind of go away. All right, let's get to the other. There we go. I don't want to have my head in the way. So if I take a look at what's going on, I know that I want to do this push here. I know that we can get the bitmap out of the element because we're going to store that. I know the UVs we can preserve. So then the real question is, how do I produce the rest of these things? We already have code that we wrote before that essentially does that. And so what I want to do here is I want to just convert to actually using that. So yeah, we've got two different ways we could be grabbing, say, the positional data. So I'm going to store, again, basically the entire information about the quad here, if that makes sense. In fact, now that I think about it, why don't I just save the quad itself? It's a very good question, and I don't know. But for example, right, this textured vertex, why don't I just save those exactly as they were? And I don't know, because that does seem like that would save me the trouble. So let's just do this. That seems a little more sane. All right. So from there, we can, yeah, like I said, we've got a bunch of options here. But essentially what we need to do is be pushing a quad on which will have these properties, and we need to set these properties somehow. Now, we know that we're not going to modify the UV ever. The UV is going to be what the UV is. So these generally should just look like this. And I guess since these are always vert, you know, the vert values are always going to get dereferenced here, I guess I don't really need to do it quite that way. I can do it like this. Oops. And the rest of these values will get set by these code paths. Another thing I could do is call this the original vertices, just to make that more clear, which seems nice. Just so nobody's, oops. So nobody's confused about that. So all this stuff mostly works the same way, right? We're just doing the standard thing we're doing here. I don't think any of this stuff really needs to change at all. The bitmap is going to switch, so I guess we do want to do loaded bitmap here. And we probably want to do that as element for rig bitmap. Like so. And then we'll set the bitmap differently if it turns out we don't want to use the original bitmap. Okay. And then, like I said in here, rather than setting these, we're going to need to store these somewhere as the p values that will then get used. Right, so here we are setting these. Then we want to set the w values. I'm not sure why this quad does not take a normal. I guess it's because it just recomputes the normal. So I guess we don't really need to worry about the normal yet. I guess. Kind of a waste of time, but whatever. All right, so then we get front emit. That should all be fine. And then when we set these colors, that'll front emit. So basically we just need our color values here. Like so. And then I need to actually define those up top. All right, so that's just going to look something like this. And now we'll see where we're at. So we need also somewhere for these to be stored. I suppose we don't need to deal with that just yet. Let's grab out that command structure because we do want to be able to get that bitmap. There we go. And now we really just need a way to drive this more sensibly. So we've got this game mode world here. If we want to, we can put in a lighting solution. And we just need that lighting solution to be defined somewhere. It should be, since it is right here, well, I guess it doesn't really matter where we define this. But point being, we need some way of triggering these things, but once we do, then we're fine. Because then we can just get them out of the, we can get the solution out of the world mode, and we can do all the rest of the operations that we wanted to do, and that's easy enough. Oops, I called it test lighting. So now we just need some way of setting these values, and we kind of need like a debug key or something to that effect in order to make this work. And I'll have to wire one of those up. But other than that, I think we're more or less okay. The one thing we did not do that we will need to do is when we are extracting the lighting, so here where we create for each one of these, where we create one of these elements, we need to store the original values that we need to reconstruct, because we're using those now, so that becomes important. And I don't know that we actually, here, don't actually know. Don't actually know where we're storing that. We zoom on up to push quad. There we go. So that'll just allow us to extract that bitmap array as well. So when we loop over this and we get the bitmaps out, we should now be able to, when we store those, maybe I'll just do that. We should be able to keep those relatively clean. What is the, oops, sorry. We should now have those bitmaps stored, and so now all we need to do is store the original vertices. So org v0 is just going to be vert0, and each one of these will get stored in turn. And I think that's it. So now we're just down to how we actually want to make this run. And we need some kind of switch that says whether we're looking at the lighting or whether we're looking at something else. And so I need to add some debug stuff there. What I feel like I might as well do, because I can't think of a reason not to, is maybe we'll just go ahead and inside our I assume this is inside the thing that says whether or not it was down before. Yeah. What I might do is just go ahead and add a little thing here that gives me the F keys as debug keys, or maybe just the number keys, basically something that allows me to send some debug keys through to the application so that they could be used and quickly hit to trigger something. So what I might do here is say, all right, let's say that, I'm just looking at it here. Yeah, let's say that in here where we've got, let's see in here where we've got sort of the catch-all, let's go ahead and say that if the VK code is greater than or equal to VK F1 and the VK code is less than or equal to VK F12, then what I'll do is I'll put into the platform input something that allows us to just set the input so that it knows that some kind of special F key went down, right? And so if I look in here, we're getting a game controller input for the keyboard controller, but we're not able to do we're not able to do the access the F key right here, which is kind of annoying. So if I look at Win32 process pending messages, which happens here, what I'd really like to be able to do is I'd like to be able to access that whole new input structure, right? And so I'd like to be able to, you know, pass it new input here, which I think shouldn't be a problem. And so I think all I should have to do is just access off of that, and we should be done. I don't think there's anything fancier to it. Like so. Where is that? F key pressed, sorry. And I do want that to also be cleared. So when we're actually doing that and doing the process pending messages, I do want to clear those out. So in here, I want to basically say like so. Once we have that, I think inside world mode, I should be able to then use that information to do my own sort of toggling here or processing however I want. So I can do a thing like show lighting, like so. And what I probably will do here is just say, well, if the world mode says that we're going to show lighting, and I guess I kind of got to reverse these two, then we're just going to output whatever our lighting solution actually was. And if we're going to compute a new lighting test, then I will say that show lighting gets turned on, like so. The other thing I want to do here is just say, like, okay, well, if we're in the mode where we're showing lighting, if the input F key pressed, let's say, it's going to be a little confusing. I guess now that I think about it, I probably should have made the F keys line up with themselves better. That way we could just say, oh, the F1 key, right? Just makes it a little clearer rather than making it quite so tortured. So if we want to do something like that, then what we can do is say, well, all right, if we're in the show lighting mode, if the F key was pressed, then we're going to get out of the show lighting mode, right? And if we're not, then the opposite is true. So if you press the F1 key, now you'll go into the show lighting mode. And I don't know if this will work, but we'll find out. P0. Ah, yes. I agree that that is a good catch. I would like to initialize those here. Oops. All right. So in theory, and I guess I don't know, but in theory, we should just start off with a purely unlit world, which it does look like is what we're doing at the moment, because it's just putting out pure colors there, which I think is what we should expect to see with no lighting. If I hit F1, it should pause for a second, which it did, and then go in here. All right, so we've got some problem with our lighting output, however. And it looks like the problem is that current quads has not been started. So we need to start the render group here, and we didn't do that. I guess that was our problem. So we're going to have to go ahead, yeah, and I guess make sure that happens. All right, so if we want to make sure that the render group actually is sort of operational at that time, although let me actually go back here just really briefly. So do we actually, we set up the render transform, do we not, or do we not? Yeah, we call set camera transform, so the camera is set up and ready to go. So I'm not sure why exactly that push quad didn't work, but I believe we should find the answer here. Let's take a look here. So I'm imagining that it's because this needs to be called. Let me take a look at get current quads. Yeah, so it looks like we need to call get current quads first before we do that process. So let me go ahead and modify output lighting to do that. So we know at the moment, because we don't really need that, we know at the moment that we need the quad count to be however many elements there are. Right now we only create one quad per element, so that should be sufficient. Let's see what happens. Well, that is certainly amusing, although not really what I had in mind, if we're honest. Yeah, not great. Not great. How we only got one of those, I am not sure. But anyway, at least we know the process is working properly, so now we just have to debug this, which hopefully will not be too onerous for us. So let's take a look here. I am out of water, which is never good. Gonna have to get 2 things of water. It's hot enough here that you just need like infinite waters. Well, probably not infinite waters. That's maybe too much waters. But yes. How much time do I have left? I feel like I can ask the bot this question. Okay, 58 minutes. So this should be easily debuggable in 58 minutes, famous last words. So the first question I have is, why are we only seeing one element? Oh, well, that's an easy one. The bitmap looks wrong as well. And I'm not sure, that may be due to the fact that we're not requesting that bitmap be cached. So there is that, but that's probably a separate, yeah. So let's maybe step in and look at the bitmap part of things here, and just see what's going on there, because that might illuminate this a little bit, because I don't really know quad bitmaps plus commands. Oh, yeah, this is not right at all. That was just me cutting and pasting stupidly. It's really that, right? So it looks like we're not clearing out that key press properly, but other than that, it looks like we're good to go. So we're almost there. So let's take a quick look If we're showing the lighting, we output the lighting, and if you press the F key, we stop showing the lighting. On the other hand, when you come through here, if the F key was pressed, you do the lighting test and set show lighting to true. That should all be fine. Win32, Handmade, F key pressed. So I think that should be clearing it. But I'm not 100% certain. Let me just verify this. What is input by itself? There you go. Well, that was that problem as well. Good. So let's see how we do now. So there is our lighting solution computed. And as you can see now, we're nicely able to rotate around it in real time because it essentially is paused. I can unpause it at any time, move to a different setup, hit it, and go, right? So that's much better because now I am freed to do things which are very expensive, which we could not possibly do in real time as tests, and still I can inspect them relatively well. And that's pretty important, right? So that's a very good thing. That is a plus. So let's go ahead and you can see kind of I'm already a little bit miffed here. You can kind of see like we just have a lot of bad, we just have a lot of erroneous things happening, which I think it'll be nice to kind of start to work on. Like, you know, why is this square completely dark, right? And why are these not bright blue? Is that just a bug in how they're getting copied out or something? Because that really doesn't make very much sense, does it? It's pretty interesting. So anyway, I think that's roughly correct. But again, I'm not sure if we introduced any bugs in the copy out. Because sometimes it can be hard to tell, especially when we don't have a working lighting solution yet. We don't necessarily know if we ruined something or if we're just seeing artifacts of our previous lighting solution. One thing I can do here is I could just go ahead and set all of the lighting equal to 1 to make sure that it's actually working. So for example, here when we're doing compute lighting and we go through this process, what I could do instead is, you know, just set front emit C equal to 1, right? I could just say so now when I hit F1, I should see essentially the same screen, right? And I do, so that's good. And that's just my way of trying to ensure that I don't have a bug in the copy out and copy back. And so at least that part I know is working properly. And so there may still be some bugs in the other parts of it, but at least that part is somewhat sane. Okay. What I really need right now is some water. I should probably get some. So in fact, you know what? I think I will get some. I'll be right back. All right. So we've got output lighting here. And now we can start to look at this just to make sure that there's nothing strange going on. I don't think there is. It looks relatively fine. And yeah, so I suspect that we mostly have a problem with our lighting, and we probably, you know, and let me say let's say I go ahead and switch it to 8 rays. Yeah, so I think we just have some bugs in our lighting there, as we expected, because it doesn't show any of those bugs when we do less rays. So it's probably just doing something stupid like accumulating and not averaging or something like this. In fact, how does that work right now? For each ray, we take the hit and we see whether we have hit or not. And then we accumulate that in. Yeah, so this doesn't really, yeah, so we have a lot of work to do here, because this is I mean, this is the problem when you just do lighting in little, like, 2-hour chunks, right? Lighting is a very complicated thing, and this is just kind of a mess. As we've just been trying things, we don't have enough time to really write out full stuff. So what you can see here as well is we don't really have any kind of sensible idea of how we're actually transmitting this light. We get a bunch of light in here and we accumulate the light. Each time through, we multiply like visibility times QC and add that in. We end up with a accumulation of light here that, as far as I can tell, this is just only using one of the rays, right? I mean, it's supposed to be that. Right? There we go. And hey, our lighting solution is a lot better now. As you might expect. So yeah, that was funny. Not sure how no one caught that, besides me. Not that it's anyone's job to catch it besides me, but you know, what can you say? So this is kind of nice at this point. It's actually starting to look kind of nice, the lighting solution there. now that we don't have an obvious error in that, you can kind of see that things are starting to propagate a little bit more nicely. But obviously we still have issues. Some of those issues are understandable, and it kind of suggests we're going to want to switch away from disks. So if you take a look at these reflectors here, you can kind of see, oh, this is weird. Oh, I guess our order of stuff that we push on here is wrong at the moment. Let's fix that, shall we? So in output lighting, I'm guessing that this P0, P1, P2, P3 that we were doing here is wrong now, and we will want to actually go in the correct winding order because we're using push quad, which will reorder them for us. So what we want to do here is say, well, let's start with, let's say, if we wanted to go counterclockwise, we'll start with positive X, we'll go to positive Y, then we'll go to negative X, negative Y. That should give us a proper disk. Oops. Go. And there now we can kind of see those disks. Anyway, what I was trying to say before I had to debug that minor inconvenience is the fact that these reflectors don't line up with the actual world is going to be more and more of a problem, which is why I think maybe we want to just go ahead and test them properly, because if you look at what happens here, you know, there's just a lot of holes in the geometry as a result of this. And we can use a larger version of the disks, but then they'll be over-inclusive of the blocking region, and you'll end up with a bunch of shadows in places that there shouldn't have been shadows, and blah, 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 blah. So we may want to kind of, you know, we may want to do something a little bit more sensible there, where we are, excuse me, where we are actually using the real quad structures themselves as reflectors, since we have so few of them. That may be sufficient. It will complicate our ray testing, obviously, but otherwise would probably be fine. So as I look through this here, you can kind of see now all the stuff I was complaining about before, now that I fixed that code to be a plus instead of an equals, you can see the stuff I was complaining about before has been fixed as well. So I'm now getting that bounce that I wanted on ground elements to a certain degree, which is nice. Like in here, you get the red twinges happening, and things like this. This little yellow dude needs to go. There we go. So like some of that bleed that I was hoping for is actually properly there now, which is good. So we've got, that was a pretty stupid bug we had in there, and I'm glad that that's gone. But again, we still have a ways to go before this code is actually doing a reasonable lighting transfer. And there's a couple things that we need to talk about. A is the multi-resolution thing, which I want to do. And now that I have the ability to do it offline, we can play around with techniques for collapsing them. But the other thing that I kind of want to do here is switch from using disk to using probably to using quads. It just seems like the right thing to do. Yeah. So there's that. And is there anything else I want to look at right now? I'm not 100% sure. I think that's mostly it. Getting the actual light transport better is something we'll want to do, but it's probably not the thing to do just yet, because we're still at the point where we need to sort of work on how we're moving that light around, and so probably the easiest thing to focus on right now is just switching to quads and then having some multi-resolution happen. That's my guess anyway. So I think that's probably what we want to do. And we can give that, I'm not sure which of those to start with. I guess probably switching to quads is the most logical one, because before I switch to quad, if I went and did the multi-resolution stuff now, we would end up in a situation where we built the multi-resolution stuff for disks, and we really don't want it for disks anyway. So it seems like maybe switching that to quads first would be the most sensible thing to do. All right, so let's now try, I'm going to go try increasing the ray count as well. I'm just interested to see. Now that we can do an extremely slow one, I'm just interested to see what the difference is there. Yeah, so I think, I guess that this is something I should probably do short term. The other thing you can see there, this is what I thought was going to happen, is we don't take into account how many things we are looking at for inbound light. So we're not really, if we cast more rays, we get higher light values, right? Which is never the right way to go. So we also need to sort of think about averaging how many samples we're taking. So the number of rays cast, right, has to be a divisor in here at the very least, because if we don't, then the more rays we cast, the more light we get, which is not a sane way to perform the solution, right? Because each one of the rays we cast needs to basically count for a certain amount of incoming light. And if we don't see anything in that direction, whatever light we see in that direction has to be multiplied by the amount of hemisphere that it's supposedly representing, that ray is supposedly representing. And so it needs to basically be a divisor on the total, right? So yeah. So anyway, just looking at how that would work, what that really means is that when we come down here and we look at this sort of addition here of front emit C, global render iteration count, essentially what we have here is this is actually the ray count times the iteration count. And now I think, if I'm not mistaken, we should get a solution that's stable across the number of rays. So depending on how many rays you want to put in, you can get different solutions in terms of perhaps quality, but you will not get a difference in terms of total amount of light. And that does seem to be the case. So there's, 8. All right, let's recompile here. So there's 16. There's 32. There's 64. And here's like our ridiculous one, 256. And you know, it seems reasonable. Right? I mean, that seems like a pretty reasonable lighting solution. And I'm not seeing too much in the way of obvious artifacting here. You know, it seems pretty good. All right. So there is one other thing I thought about, and maybe this is something we should address sooner rather than later, actually, now that I think about it. And that is that we also need a way of smoothing out the light solution. And we haven't really talked about that yet either. Smoothing out the light solution just means that if you look at what's happening here, we're only computing the lighting for reflectors on a per face basis. What this means is that the lighting would always be very blocky and wouldn't have a lot of gradation to it. And you can probably understand why that's maybe not the best possible circumstance for us here, and it's unclear what we necessarily want to do about that, right? So the question becomes, how are we actually going to deal with reconstructing an end lighting state from one of these lighting computations? Meaning, once we've computed what the lighting is supposed to be, how do we then actually have the pixels in the game look up into that lighting solution to produce some kind of a smooth result? If you imagine this scene right here, what we'd want to do is for this to be a sort of, this should sort of be a radial gradient looking like thing. And of course, at the moment, it definitely isn't. It's just, you know, all we've got is sort of a way to reproduce sort of the blocky version of that. So there's a couple different ways we could imagine attacking this problem. And it's not immediately clear anyway what the best way to do it would be. So one way to do it would be to actually try per pixel to have some kind of a lighting query that looks up into the world and uses the computed lighting on the reflectors to figure out what the lighting at the pixel is. I don't really know how effective that would be. Maybe it's theoretically possible that that would just work, meaning if there was some kind of a multi-resolution query where it just kind of looked up the reflectors in its immediate vicinity and did some kind of a blend between the nearby ones based on its normal, maybe I could see that working. I have to admit it's a little bit scary sounding, like I don't know for sure that that would actually work. So that's a little bit dicey. The other way we could imagine doing it is we could just be computing these at a little bit of a higher sampling density. So instead of just using one reflector per quad, we could use one reflector per vertex per quad, which would at least give us a little more lighting fidelity, like a little bit more. So you could imagine dicing this quad up into essentially 4 quads and setting the lighting based on which, you know, this vertex's lighting would be based on this reflector's incoming radiance, right? I'm not sure what to say about that. It has some attractive qualities, namely that there's no per pixel cost associated with the lighting. It's a more flat cost. And it just has an obvious way in which you get the lighting from the light solution down to the actual drawing. The problem with it is that any lighting that's based on per-vertex is always going to fall victim to the sampling density that you use. So it does seem like it's probably not going to be a particularly high quality method of reproducing the lighting. And we probably could do something better given the information that we have. So again, I would say it's a tricky situation. And I don't really know what the easiest way to try to make that work would be. A per pixel lookup for color information. A per pixel lookup for color information. I guess now that I think about it, it's not entirely out of the question that that could work. Like, maybe it just would. So this is a bit of a quandary. I really don't know. But I think that the saving grace here is that once we have this information, we can put it in a spatially coherent structure. So for example, once we've done the reflectivity, we could put it into some kind of a voxel or any other sort of lookup structure we want. And then every pixel could just interpolate the lighting based on what it found in the neighborhood of itself, right? It's really tough. This is always the problem with anything where you're trying to reconstruct lighting with less than per pixel accurate results. You end up in this situation, you see people try to do a lot of clever stuff like with temporal anti-aliasing or screen space ambient occlusions or screen space reflections and all these sorts of things. You always end up in the same sorts of predicaments where you're just like, well, you know, we've got this problem where we are trying to reconstruct things at pixels, but we don't have the actual data of what happened at the pixels. We just have data about what happened in some other kind of sparse way, and we're trying to reconstruct something that's going to be good enough, and it always has bugs and edge cases and whatever. And I think this is one of those kind of things. So I just don't know. I really don't know. I mean, here's what I would say. It wouldn't be too hard for us to try doing this per-vertex. So, for example, if I wanted to, what I could do here is say, well, for each one of these, I'll create one of these lighting elements per vertex. And then when I come back through, when I do the output lighting, I could actually take the color per vertex and put it in here. So we could actually test per vertex lighting. It would not be too difficult to test per vertex lighting. And again, the problem that I see with that is just that per vertex lighting doesn't really produce the kinds of results that you want for lighting that changes within a quad. it can only do kind of a constant gradient wash. Maybe that's good enough. I don't know. I suspect it will probably have some obvious artifacts, but we could test it pretty easily. So I guess we could kind of do a test here where we do that. I guess maybe let's just see what happens if I break this up into multiple routines. So extract lighting from quads, extract reflectors, I should say. So we'll do extract reflectors from quads and extract reflectors from verts. And so if I wanted to be able to do either of those two things, close pick index, I don't really care about anymore. There we go. So when we do lighting copy in, let's go ahead and grab this out. Here's the quad version. And let's go and grab this part here. Okay, so if we imagine that we want two of these, one that would be per quad and one that would be per vertex, then extract reflectors from quads is going to do the same path that we were doing before. Presumably, we can just make that compile fairly directly. And then what we need to do, excuse me, is make sure that all the rest of these things can operate in either fashion. So here. There we go. So now really it's just a question of we have to make sure that we call one of these first to get the information. I don't think debug light P is used anymore. It's just camera P that's used. So that should be good. So what we want to be able to do now is say, well, okay, we want to be able to do an extraction from the vertices. If we do an extraction from the vertices, the tricky part is just going to be that when we output the lighting, it's going to be kind of confusing, right? Because it's going to have to do sort of an integration here where it takes 4 reflectors and packs them separately into one output quad, right? So that's going to be kind of the nastier part of it, but we'll ignore that for the temporary moment and just focus on the extracting, since that's going to have to happen as well. So here's the extraction code, and that's operating currently. If we wanted to make this extract per vertex, then as we come through here, and we are about to output a lighting element. Really what we want to do is output 4 lighting elements, right? So this quad count here is going to be 4 times, like so. And the lighting element is going to have to be something that happens 4 times, right? So here's our loop, I guess. Element index less than 4 plus element index. And I think what we want to do here is just say, well, all right, so instead of half of the span, really I guess what we're going to do here is it's going to be a quarter of the span is going to be the actual length, or I guess I should say, since we're oversampling, you know, a third of the span. And the location is going to be one of the vertices. Right, so it's going to be whichever one of these we're currently on. I guess that means we sort of have to do this as an array, because I'm going to want to do something like this. Yeah. It's not pretty. Admittedly. So yeah, that should do it. And then if I just say we've got vert p4 here, we get all of those, and then we can compute them thusly. So if we take each of those, we can now grab the center out properly. The radius is just always going to be the radius. We can just, it's the same radius for everybody, so that's not really relevant. It's the same color for everyone as well. That's just uniform computation. Oh, no, actually, it's not. We can do better than that now, because we can actually just get the color for that particular vertex. Same would be true of the normal. So all of these can actually access those directly now. All of this stuff seems relatively straightforward. Again, the emission, same thing here. And then the only problem is these values are not really accurate anymore, right? But otherwise, I think we're good there. So now we should be able to do this, although we may need to make that array bigger. But if we want to just look at reflectors, we should now, in theory, be able to do that, I think. Of course, the other thing I probably should do is set that value down from 256, since we don't really need to see that at the moment. But so here's what it says the lighting solution is. That doesn't really make much sense. It doesn't look like we've got one at every vertex at the moment. Or, well, actually, maybe it kind of does, but they don't look large enough. What's going on here? And also, I guess I do have to do an offset, now that I think about it. This is going to be a little more complicated if I actually want to plate this properly. So we just make sure we can run this relatively quickly. It should be pretty cheap. Ooh. Forgot we are not set up to do that yet. So yeah. It kind of looks more to me like we're not really distributing these at the vertices at all. I'm not sure what's going on there, so let's take a look at what the problem is. So we're getting the vert p values. This looks reasonable to me. And then we're accessing out of the vert p for whatever element index we're on. Oh, pfft. Somehow that snuck outside the brace. So we were, in fact, not creating 4 of those. Let's try that one more time. There we go. All right. So at least now we're creating 4 of them. We're not creating them correctly, however, for a number of different reasons. So I still think, yeah, we've still got a bunch of bugs in there. All right, so let's take a look at this. So we're going through the elements 0 to 4. We're picking out, and perhaps instead of element index, that's really not right. It's the vertex that we're talking about here, right? The position should be correct because we're not even trying to move that to center it about the face yet. So how that's wrong, I don't know, but it kind of looked like it was wrong. So that's a bit strange, but oh well. So position and radius of the reflector. None of this stuff should matter at all, nor should any of this stuff because we're not using it. So it's really just these 2 things, and I'm not sure how that's managing to be so incorrect. So just to give you a little bit of an understanding of what I'm thinking about here. So if we imagine I mean, I guess I could convince myself that was correct. I can't really. I mean, I guess I could imagine that that was correct. So if we take a look at this as one here, here's all the vertices. At each vertex, we do have the different reflectors pointing in the various directions. Okay, you know what? Maybe I can convince myself that's correct. Let's let myself temporarily believe that that could be true. And then what I'll do is I'll do the code for actually offsetting these, and we'll see what happens. So if you look at what's got to happen here, we've got 4 vertices that we're setting. And really the positions of those vertices are pretty different. What I probably didn't need to do this in hindsight because I'm going to have to do each of these manually. Although we still probably could come up with a different an algorithm for setting them, actually, but, you know, we'll see. Anyway, so if we imagine each one of these vertices like so, if we're imagining this as a quad, then we know what our bases are, right? We know that we have, if I remember correctly, we've set these up. They're coming out in tri-strip. Oh, we've done it. We've untri-stripped them. It looks like here, right? So we do 0, 1, 3, 2. So we've got presumably this. And so we did 0, 1, 3, 2 to return to a standard kind of ordering here. So what we want to do is we want to create a set of reflectors that represents this face, and we want to distribute them across the surface evenly, right? So what we want to do is say, okay, the vertex reflector for vertex 0 wants to be like right here. And the vertex reflector for vertex 2 wants to be right here. Which means that 1/4 of the span from 0 to 2 should be added in, and 1/4 of the span from 0 to 1 should be added in for the vert 0 reflector, right? Does that make sense? So they can all be based off of vert 0 if we want, right? They can all be like vert 0. And then we just want to do, okay, whatever the span is, and don't ask me why I called these that way. Usually I name them from, to, and from, but that's all right. It's fine. So if I want to do that, I need to add in 1/4 of the span from 1 to 0, and 1/4 of the span from 2 to 0. Well, like I said, we renumbered these, so actually it's 3. Right? And what we need to do here is each of these is going to be a different span amount, right? So, and if we wanted to, we could base them. We could make all of these be 25% by using the span in question. So if we redraw this with the things actually renumbered, the way we renumber them, so 0, 1, 2, 3, then the vert 1 version is going to want to go, well, I guess we technically never compute that span, but we can use the span from 0 to 3 instead, right? So it's going to want to go 25% along that one, but it's going to want to go the negative 25% along the 1, 0 span, to put it like right here. For element 2, which is this one, it's going to want to go a negative on both of those. And for 3, it's going to want to go a positive on the 1, 0 span, but a negative on the 3, 0 span. Oops, got one there. All right, so let's take a look at that. So as you can see, that did produce a fairly regular tiling. So I guess I can convince myself that I didn't have the bug. And so you can see now how this produces potentially a better lighting solution. Because now we, at each vertex, could get some lighting that was potentially more accurate. So let's see if we can do that now. When we do output lighting, you can see us going through the elements here. And what we really want to do is say, well, instead of going through the elements one at a time like that, what we actually want to do is we want to go through the elements by 4s, because we're only going to output one element per. We're only going to output one quad per element, right? That's effectively what we're saying. So what we want to do here is kind of wonky. But, you know, what can I say? It's just the way it is. So what we're going to want to do here is we're going to want to say that in this path, right? In fact, I guess maybe we have to get kind of a light computation thing happening here, where you can kind of see that we've got this I guess what I'm saying is I think we almost want to write a separate routine, how we had output lighting, you know, output quad lighting and output vert lighting, basically. Like so. And then what I can do is just pick which one of those I'm doing. So if I wanted to have the one that does the vertices, the one that does the vertices is going to do the element count divided by 4 as it goes through. And what we're going to do here is just say, yeah, we don't care about show visibility anymore. And we don't care about show reflectors anymore, because we would be calling the other path if we were doing that. So we could do if show reflectors, then go to the quad path, otherwise go to the vert path. Okay, so the vert path needs to be able to do this. And what we want to do here is we want to effectively access, in fact, you know what, we probably want to do it like this. So we grab out one of the elements, and most of this code is actually will still work. But what we want to do is, instead of doing the Handmade product with just one front emit, we actually need to grab all the different front emits, right? So we need to be able to do element 0, 1, 2, 3, 0, 1, 2, 3. And we're kind of relying on the duplicated data, because inside each of those, they store all the original vertices just in a fatty way. They just store them all. So we can just rely on it. And so what we can do here is do a thing where we say, like, okay, let's grab out each of the front emission values, and then we can pack the vertices with different Handmade products on each one. And I think that might be all we actually need to do. I'm not sure. So here's the reflector computation. Here's the lighting computation without the reflectors. Not so good. Oh, I suppose also, plus equals 0. That was good. I suppose we also want to say that this is going to be divided by 4, because we're only outputting a quad every 4 elements now. So if I go into the renderer, let's try this now. Show reflector is false. So you can kind of see it gets a little better, but you can also see some of the problems with that. I mean, we don't necessarily know, there might be some bugs in there, but you can see sort of those banding artifacts from the vertex-based lighting. That was exactly the kind of thing that I would be afraid of. Let me just move the lighting over here so you can kind of see. And that's just because, again, if you take a look at the reflectors, generally have some pattern of what's dark and what's light, and then they're just going to get interpolated in a straight linear fashion, right? And so that's when you get that kind of ugly vertex-based banding. So basically what happens there is you're almost good. I mean, it almost looks good, right? So it's not like the worst thing in the world. And like in some cases like that, when the vertices happen to line up with the sampling, it actually looks quite nice. Like this right here looks great. Ship it. But when you get those problems, such as in this example, you really get some nasty banding in there. So I think we would want to come up with a solution to fix that anyway, if that makes sense. All right, so let's go ahead and go to the Q&A for now. We've done everything that I wanted to do today. Tomorrow we can maybe look at what we want to do about the banding, or we can move on to the multi-resolution stuff that I'd like to do, either or. You can triangle order the verts for the banding issue. Oh, I think I know what you're well, I guess I don't know. I'm going to try and guess what that means. Do you mean that since you can pick which one of these two you want to do, if you have, if you look at the 4 vertices and want to know and have an opinion about which way would produce the least ugly result, you pick between these two? Is that what you're saying? And I mean, I agree it might help a little. I don't think that's going to get us all the way there. It's hard to say. Like, I mean, if I look at what's happening, say here, no matter which way you pick it, you're probably going to get something relatively ugly. It just feels like. So I don't know that that's really attacking enough of the problem. Like, I think you would get if you swapped the order of this triangle, for example, you'd just get a bright band with a dark edge instead of a dark band with a bright edge. So I don't really think that's going to solve the problem much. The problem is that it's undersampled, not that it just happens to have one of the rotations. Brian, the hardware render is running right now. It's just the lighting is happening in software. Gary Johansson. So I have the idea of maintaining all geometry in a geometrically determined hash table computing the trajectory of the reflections and looking up where the resulting geometry. Is that something that would be workable, or am I missing something? So I don't necessarily know if you're missing something or not just from the question. It depends on how you're thinking about it. Let me just give you some food for thought there, and then you can decide for yourself whether you're missing something. A geometrically determined hash table is a hash table that basically takes some kind of an input position, like say x, y, z, and hashes it to a particular value, you know, some 32-bit value or something, so that you can then look it up in a hash table and see whether there's anything else that matches this x, y, z, right? So the problem with this is that it's very good for if you just have points and you want to know whether you've seen a particular point before. That can be pretty handy, right? But with something like lighting, what you're typically doing is looking at volumes through space, like lines through space, or cones through space, right? And this makes geometric hashing a lot harder. The reason it makes geometric hashing a lot harder is because how do you define a line through space, right? Well, a line through space is going to have to be parameterized somehow. So one way you could do it is parameterized based on just the normal. But if you think about it, that's really not enough, because just the normal doesn't tell you, that only gives you the lines through space that happen from the origin. You really need a point plus a normal to define a raycast, right? But if you want all of the things that lie along this line in space, then what you need to do is come up with a canonicalized way of representing P. N can just be the normal that you're looking for, but P would have to be some canonical representation. Now that's not so hard, right? You could probably figure out a way to canonicalize P so that any line in space could then be represented in this way, right? That's not that hard. We could figure out ways to do that. So I agree that we could get a hash table that was like px, py, pz, nx, ny, nz, and really, really this is overdetermined. Really, you only need two of these. So to be a little more explicit here, if you imagine what we're doing here, if you take the origin, and we'll just do it in 2D because it's easier for you to visualize. So let's suppose we were just doing this in 2D. So here's the 2D grid, and I take a particular normal that goes in a direction, right? Here's the normal that goes in a direction. And what I want to do is I want to say, well, okay, from the origin, all I would need is a normal x, normal y. All I would need is that. And really, even that's overdetermined. I could just use a theta. I could use one value that would tell me what the angle was, and I'd be done. But now the question is, what if I wanted to represent, say, lines through space that started here, right? This line through space cannot be represented by any value that we just put here. So what I need to do in 2D is I need to introduce one more variable, which is the amount of slide relative to the perpendicular to that, right? So the perp of n going in the opposite direction, perpendicular direction, I need to introduce a displacement along that so that if I wanted to represent this, I would start with this, which I can represent, and then produce d along this to bring it to here, right? So I definitely can produce those things. So that gives me something I can look up into my hash table so that for every line through space, I can get a hash on that line in space. Now here comes the problem. The problem is, well, what do you put into that hash table? What do you put into it? Suppose that I have a thing that I would like to hit. And so I want any line through space to have that, you know, to have this be in that hash. Well, there's an infinite number of lines that hit that thing. So I can't very well hash this way, right? So that, I think, immediately disqualifies you from doing any kind of hashing based around the actual lookup you're doing. So that means you would then have to go and say, all right, the kind of hash I'm going to do instead is a hash based on, say, some kind of spatial occupancy. So if this thing that I'm talking about happens to be in this region, I will hash it with this point. So it's like a discrete hash, right? It's basically a sparse voxel at that point. That's all your hash table is. And again, the problem is now, how do you cast against it? Well, if I'm going to cast against it, I now have to cast through a sparse voxel. If it's a hash table, I don't even have any structure to the sparse voxel, so I'm going to have to cast through every voxel point, looking up along the way the query as I go, right? Looking to see if there's anything in there. And again, I would say, why not just use a sparse octree, right? Why not just use something with more structure so that you can move your array along faster or something, right? So I guess what I would say is, I don't know, does that cover the ways you were thinking about it? And do you still think that that would be productive or not? If the answer is that doesn't cover the way you're thinking about it, tell me what that way was and I'll take a look at that. If it does cover the way you're thinking about it, and you don't think that that means that it wouldn't be a very good way to do it, then you have answered your question that no, you are not missing something. If, however, you now no longer think it's a good idea, then I guess the answer was you were missing something, I guess. Why is my chat not updating? Oh man, did I get disconnected again? My hex chat has been really not working. Like, really not working. It used to work just fine, and now it doesn't work hardly at all. I don't know what happened, but it like constantly disconnects and I miss messages now. So I'm sorry, if you asked a question after Gary Johansson's, I have not seen it because HexChat decided to not talk to the server anymore, because why not? Yeah, this is a Linux machine, so I can definitely switch to WeChat if it works well. I could try that. I would be happy to try a new one because HexChat has been really unreliable. And there's nothing in particular that I like about it. I mean, I'm just using it to view the chat, so I don't need, like, I just need something that will be reliable. It doesn't have to be fancy. Criminator 117, yeah, those vertex banding patterns that you see are very distinct, and they are just, that is what happens when you just interpolate along points in space linearly and don't do any recomputation inside, is you get these linear bands because that's what should happen. It's correct. Unfortunately, it's not pleasing, And so if you're relying on that to generate some kind of nice results for you, a lot of times it won't. It's why Phong shading is better than Garot shading, for example. Derpzerker, would it be possible to write a transpiler so that we could take the C code and run it on the GPU trivially after debugging on the CPU? Yes and no. So the primary problem, and the reason why I wanted to do it on the CPU rather in the first place, is that the kinds of things that run fast on GPUs are not the same as the things that run fast on CPUs necessarily. Or maybe I should state that the other way around. Because typically if you do have something that runs fast on a GPU, it will run fast on a CPU as well. What I more meant to say was CPUs can do a lot of things GPUs can't, right? GPUs are set up very specifically for low clock rate, narrow cache, like highly memory coherent workloads that are wide, SIMD very wide, right? And I don't want to have to think about how to make the lighting code work properly under those constraints yet. So it's not that we couldn't make exactly what we write run on the GPU, because GPUs are pretty general purpose these days, so we could get that to work. The problem is we wouldn't want to, right? The problem is what we want to do is get the lighting solution working nicely here, then do a pass where we rewrite it to be efficient and streamed properly for a GPU setting. And so, yeah, I wish there was a way that that could automatically happen, but it's not really something that can be automated at this point. ChaosCom, in your lighting formula, you use negative spans like negative span 1, 0. What if everything is supposed to be a displacement of vert 0, shouldn't you have plus 0.75 at some point instead of something negative? Yes, but remember, I didn't base it off of vertex 0. I ended up basing it off of whatever vertex we were actually trying to put ourselves on, right? That's why. If I had based it off vertex 0, then yeah, they would be 0.75 and so on. You're using a square, so why not filter bilinearly along the square axes rather than interpolating over the triangles? That should avoid the diagonal seams. Not... Oh, okay. I think I see what you're saying. So you're basically saying do a UV interpolation style, like a what's the word I'm looking for? So if I'm catching you correctly, you're asking, could we do something like this? So right now what's happening is the graphics card is drawing these like so. So what it's doing is it's interpolating, you know, here to here, here to here, and here to here, right? So basically, like, as it walks down this line, it's just interpolating down to this value, right? What you're asking is, would it improve matters if instead we did a bilinear where first we produced the blend between these two, and then we produced the blend between here, right? At least I think that's what you're asking. And the answer there is it might. it might improve things. And unfortunately, I'm not sure exactly how to test that quickly. Because we are sort of forced to go through the standard rendering pipeline here, I think what we would have to do is sort of in our pixel shader, we'd have to output these 4 values into the pixel shader per vertex, so that when it was interpolating them, the pixel shader could instead do the interpolation, right? Like I said, I don't think it's a bad idea. We can't really test it right now, right? But I do think it's a reasonable idea. Maybe we could try it tomorrow. So. And yeah, ChaosCom, it's true that light doesn't behave linearly, but remember, we only really care about whether it looks okay. We don't care how accurate it is. We just care that it looks like it's behaving light-like. So if we get a good enough result in terms of visual quality, it's okay if it's not really all that related to what the real lighting solution should be. So I'm certainly willing to try if we could make a different interpolation mechanism that eliminated the banding and just produced relatively nice results. Then that would be a win, I think. It doesn't, maybe this particular one won't work, but that doesn't mean that something wouldn't work, right? And so it is an area that's worth examining, to say the least. But, all right, I'm going to go ahead and wrap it up. Actually, I should close some of these down. Goodbye. Bye. All right. Thank you, everyone, for joining me for an episode of Handmade Hero. It's my pleasure coding with you, as always. If you would like to follow along at home, you can always pre-order the game on handmadehero.org. It comes with the source code, so you can test out things for yourself. We also have a forum site you can go to if you want to ask questions, a Patreon page if you want to support the video series, a schedule bot that tweets the schedule at you, an episode guide that you can use to catch up on past episodes, and of course, a little button that you can use to view the show. It's not live now. It will be live, if I refresh the page, it will be live in 20 hours. And that is true. We will be back tomorrow for some more light coding. Hopefully, everything worked fine from the new streaming setup. I didn't hear anyone say that the stream went down, so that seems pretty good. But that's about it. Until then, have fun programming, and I'll see everyone on the internet. Take it easy, everybody.